There we go. Give it a minute here and see if anyone else shows up. Well, why don't we go ahead and get underway here? So let's see. Okay, where do we leave off here? Well, I guess where you left off was actually with Jonathan, who was talking about time to event outcomes. And I wanted to step back and go into a little more detail on some of the other sort of categories of non-standard or at least non-continuous outcomes, and the sorts of summary statistics that get reported for those, and how we want to do some model-based meta-analysis when we encounter those kinds of outcomes. So let's go back. Let's start out with the binary case. Good. Bring this up full screen. So you've seen this before, actually. We talked briefly about, how do we deal with cases where what gets reported is something like either the number or fraction of patients that experience some particular outcome or event. So this could often be some, like a responder status, or some count of the patients that experience an event like death or MI or some such within the studies. And so when we at the individual level analysis, these are simply binary outcomes, but when reported in the literature, the summary measures are usually either some count, fraction, or percent of patients that experience those particular events. So how would we deal with that? And as I said then, probably the most appropriate likelihood function for the number of patients with some particular outcome would be a binomial distribution, since we're basically we've got a finite set of patients. So if in binomial terms, we're talking about you've got if you've got n patients, and you've basically got n trials, and you have so many successes if you count these events as successes in here. So that's logically described by a binomial distribution. As I mentioned here, that's parameterized in terms of the probability of an outcome in any given individual, and then the total number of individuals. So I just called it P and N in this case. And that probability is typically a function of various independent variables, and in our case, typically that's going to involve some measure of drug exposure, whether it be dose or concentration. Time may also show up independently in that, and maybe some sort of mean measures of demographic variables, age, weight, so on. And of course, P, it represents a probability, and since it is a probability, it has to be restricted to the interval 0 to 1. Once we get past that, there's not a whole lot we can do to generalize about any specific function for P, although a particularly common category of models that's used to deal with that and to enforce that 0-1 restriction is to use logistic regression, in which a logit transform comes into play, because if you apply the logit transform to something restricted to 0-1, that then transforms it into a number that can be anywhere on the real line. So let's take a look at an example. In fact, that's really what I'll be doing primarily today, is going over a couple specific examples, and one of them for this for the binary outcome case. Actually, before we even jump into that, I forgot there are a couple of things that I probably should have mentioned right at the outset. I had promised to have a midterm exam ready, and it isn't yet. One where the hook by hook or crook, I'm going to have something to you by the end of this week in order to do that. So that will happen. I haven't heard any comments one way or the other about the proposal I made to change the course requirements to just a midterm and a problem-based final rather than also incorporating a project of your own choosing as part of this. So unless I hear otherwise, that's what I'll be assuming that we're doing for the course grade. Just mention the last meeting of the class. Looks like that will probably be on the 5th of May. So that's what that means we'll have this class plus 2 more, and that will be the end of the actual meeting sessions in here. So, and sometime in the neighborhood of that last meeting, then I will post the problems for the final. Let's see, was that it? Yeah, I think that was the only extra announcements I had there. Okay, so let's jump into an example. The example I've got here is the data, at least most of this data, I believe is, let's see, this is actually real data in this instance from various articles describing the use of factor Xa inhibitors to prevent postoperative venous thromboemboli. That's the VTEs mentioned here. And you can see here the various drugs represented in this plot here. We've got apixaban, a Lilly product here, risaxaban, rivaroxaban, and another drug here, YM150. I forget whose that is. And these are all plotted as fraction of patients that experience a VTE versus the dose of those particular agents. So in this case, I've sort of selected from dose response studies for these various compounds. And we're going to be looking at modeling those dose response relationships. In addition to the blue curves, which represent the drug that's mentioned in the panel label, for each one of these studies, enoxaparin was used as the reference treatment, as the active control. None of them had a placebo control I presume the reason anyway is probably an ethical one. It's the VTE rates are actually rather high for certain types of surgeries. In this case, they are. This is a mix of studies with either total knee replacement or a hip replacement in these particular ones, and it's high enough that it would be considered unethical to let the patients go untreated for preventing those VTEs. Anyway, the red horizontal lines on each of these represent the fraction of patients that experience VTEs that were on that reference treatment, the enoxaparin. So we're going to be then analyzing that data. Let's see, is there anything more I want to say about what's on here? Let's see. That's pretty much the story for that slide. So we're going to throw out a proposed model here. Of course, ideally, we'd be going through some sort of probably a model exploration and selection process here, but I'll just throw out an illustration of a model that could be used to describe the data. The model I'm going to use, it's going to be a linear logistic regression model, but since the values we have are not the individual binary outcomes, we're not going to be using a Bernoulli distribution. We're instead going to be counting up the total number of events across, or actually counting up the patients with events, and that becomes the value we're going to use relative to the total number of patients in the group. So we've got our number of patients that experience a VTE. So the I and the J here represent the I correspond as an indicator for the treatment arm and J for the study. So we're talking about the number of VTEs in the ith arm of the J study. And that will be distributed according to binomial distribution with some probability for the VTE that may vary as a function of the different treatment arms and the total number of patients in each one of those treatment arms. For the model here, I chose a one where I'll just describe the logit of that probability. So again, that's converting the 0 to 1 range out to the entire real line. This is going to be a sum of a component here. I put a P here, thinking of it as essentially being a placebo outcome, and then added to that a drug effect over the top of that. For the drug effect here, I chose a sort of a variation around a linear model. This was, in this particular case, it fit better than a model that was linear with respect to dose. Here's went with, you've got a parameter to be estimated here, theta sub drug, times the log of dose plus 1. The rationale behind the dose plus 1 in there is, notice that when you're taking the log, if dose is 0, you end up with the log of 1 or 0, so that E drug will be 0 in the case where the dose is 0. So the log was chosen just to come up with a shape that seemed to describe the relationships better than a straight line, and the plus 1 again is just to force the function to be 0 when the dose is 0. And then finally, the placebo effect is just modeled as a constant term that can vary from one study to another. So so you can see it's EP sub J, not sub IJ. So that value is constant for a given study, the way this is being modeled. And the inter-study variation is being modeled as normal for that. So let's see, is there anything else in the definitions here? I think we pretty well hit definitions for NBTE, N, I, and J. Okay. And of course, we've got to well, actually, before I go any further here, any questions at this point around, either the data or the model structure that we're applying here? Okay, nothing so far. I'll keep on moving here. So went with a very weakly informative prior then for the slope term for the drug effect, and this was actually done, by the way, is I actually stole this particular example from our MI255 course, and where at the time I was also interested in illustrating the use of informative priors as part of this. But what I've got here is actually a fairly informative prior for the placebo effect in this. As I say here, it's actually completely fictional, but it illustrates the idea of maybe using historical knowledge about control treatment response. And you probably could, in fact, go back to earlier trials that were done before there was an established use of things like enoxaparin or other anticoagulants for this problem, and you might be able to construct from that some historical information about the placebo response and then incorporate that into this. In this case, I didn't make that effort. This was purely contrived, but it just illustrates how one might incorporate prior information, but prior information that still also reflects your uncertainty in that prior information and how it applies to a modern context. So anyway, so what we've got here then for this theta p, the mean here, just got something which is normally distributed, and you can see it's centered about this logit of 0.45, which is another way of saying that sort of the typical value for the fraction of events in the placebo group would be 45% is the way that's set up, with some variance term on here. And then in turn, the inter-trial variation here, you can see is written in terms of this log of 0.4 around that value. So again, this is I would call it sort of a moderately informative prior regarding the placebo outcomes. Again, potentially useful in a context like this where you actually have no placebo treatment in our data. Let's see, do I want to show it here? I'm trying to remember if I changed anything when I moved this over. Let's actually, at this point, jump to the actual files here. This is something I posted on the website where we've got this particular example. It was called binomial MEE example. The reason for the name, by the way, was in the context of MI255. I was talking about binomial mixed effects models, thus the binomial ME. And let's go ahead and open up the model. And oh, I opened up the R script. Let's try the model. Okay, here we go. Okay, so where do we go here? So the core of our model is going to be right here. So I've got, so it says for I in 1 to n obs. In this case, the number of observations is also equivalent to the number of treatment arms, since we're not dealing with longitudinal data. We only have one observation per treatment arm. So let's go back to our model here in sort of mathematical terms. So we've got this number of VTEs, or number of patients with VTEs, being binomially distributed, and you can see exactly that same relationship right here. The way this is going to be set up when you see the R script is the observed values are being passed as counts of patients as opposed to fraction or percent of patients. So this VTE term right here will represent the number of patients with a VTE, and that's binomial, and in BUGS that's just written as DBIN, with our probability of an event and the total number of patients at risk for that event in here. Again, the I here is looping over all the treatment arms. Then let's see, let's go to, actually let's skip that line here and just look at these first. So right here, you can see where it's got the logit of that probability is the sum of a placebo and a drug effect component here. The drug effect component right here. So we've got our drug effect is going to be our parameter theta. And I guess I didn't mention the theta would be drug specific. So we've got, I forget how many, what do we have, 4 or 5 different drugs in here. So there will be, in fact, we probably got it, I guess I have 6 different drugs, because down here we're actually setting it up. So we've got 6 different possible drugs. So drug will have to be passed as a data item and take on a value of between 1 and 6. in here. And again, that's multiplying log of the dose plus 1. Part of this. And let's see, what else do I need to mention in here? Okay, that's really the core of the model. And then in addition, we have the inter-study variation on the placebo component here. So that value is being generated in the second loop over here that loops over the study. Again, that's where our normally distributed inter-study variation in that intercept term is created. So that's really the core of it. We've also got the usual individual prediction value here. So here it's going to generate a predicted number of patients with a VTE corresponding to each one of the observations here. And notice the right-hand side again is identical to what it is for the likelihood component. And down here doing the same sort of thing for our population predictions over here. So in addition to having the main likelihood statement there, we also have to generate any components that depend upon any study-specific values in here. And in that case, we only need to do that with the one particular line. And then our priors, there's probably nothing too much new to be said in that, other than we've got you can see how where'd we go here? Make sure you get the right bits, how we've got sort of the informative prior associated with the placebo effect is generated down here, and the rest of it is fairly familiar territory, comparable to what we've done with other studies where we've had weekly informative priors. The script associated with that is probably not too much new in that. It's got the usual boilerplate on it. You've got the model name here, various packages in that we pull in. The data set, I guess I should show you the data set. It's right here, fxa metadata.csv. Open that up. Get a bit bigger here. I see this has got a few vestigial parts in here that aren't going to be too useful to you, but we've got, you can see the various drugs that are represented in that data set, the daily dose of each of those. In our case, we weren't using frequency as part of our model, so we're just going to use daily dose, but I do have the frequency captured. Treatment duration, again, in the model I've got here, hasn't been used. Actually, is that? Yeah. It's the treatment duration as well as the observation duration, which is probably even the more critical one. As I say, there were two surgeries represented, either total knee replacement or total hip replacement, and that's why you see something called TKR and THR in here. In the model I'm doing right here, I'm lumping them together and not trying to characterize the differences. Actually, in a context where I actually did this in a production context, the type of surgery was a significant covariate. I forget which one is which, but one of them does tend to result in a higher incidence of VTEs than the other. So ideally, this model, I would view the model that I'm showing you here as maybe a sort of a preliminary or base model that probably ought to be refined by looking at covariates such as the type of surgery. The actual data set here has a variety of types of events here. In particular, it has a mix of VTE events as well as different categories of bleeding events, but we're only going to be using the VTE events. What we're doing here, I suppose if you wanted to have some fun, you could also take a look at the bleed events. Again, those are measured as number of patients experiencing a particular category of bleed event, and you could model those also using a similar approach. The the events here then represents the number of events per treatment arm out of, and then the N is the total number. So I'm sorry, I say number of events, although in this case that's really equivalent to number of patients. So it's actually really the number of patients experiencing that particular kind of event. N is the total number of patients at risk in that arm. And then I have a study identifier here. There was a reference number here, but I've long since lost track of the bibliography for that, so we'll just ignore that. Okay, so that's the data set we're working with, and I guess what? We're only going to be using drug, dose, well, we're going to split out, we're going to use event type just to split out the VTEs. We're going to use events. Essentially, events here is equivalent to what was called VTE in the model. And N we'll certainly use, as well as the study identifier. So all of those are in there. Okay, so but anyway, you can see this is being pulled in. This statement is just used to calculate the fraction of patients that experience an event that actually isn't used in the model, but is used for some of the plots in here. Let's see, we're creating the WinBUGS data set. Here it's just picking out, here's where I pick off only the VTE events, as well as only a subset of the columns that we might use in the model. This is just a little bit of data management to deal with the fact that one of the trials actually had both types of events, and I was just lumping them together into a single count for a given treatment arm. So it pulls all of that together down here, and finally, based upon that, pulling together the data set. Not a whole lot to say here. Maybe point out this is where the information about what drug it is converted to an integer from 1 to 6. In fact, you can see the matchups here. Then enoxaparin is 1, rivaroxaban 2, and so on in this list. Initial estimates, nothing too interesting there. Maybe I'll mention, this might be worth mentioning no, that's actually not worth mentioning, never mind. Yeah, most of that's all pretty familiar stuff. Let me go ahead, actually let me just temporarily rename this so it doesn't get overwritten in case we need it. Let's just go ahead and fire this thing off. As I recall, this one doesn't take too long to run, unlike the next one we'll be doing. Oh, I guess I forgot to fire up an R thing there. Okay, so I think this will just take a moment here. I just noticed probably the version I sent out to you is probably the same as this one, and it's set up with the course directory assigned to the name that I use on my machine. Yeah, it doesn't take very long at all. It's already done. So you'll want to, oops. Oh, that's right. You'll want to, where I've got here is course dir equals, this file path with home and project slash MI260W, comment that line out to make it work on your machine. Okay, so it seems to have finished. Okay, let's go ahead and exit and let it finish. Okay, are we done? Okay, yeah, looks like it's done. Okay, so let's take a peek here. So our history plots are more or less fuzzy caterpillars, nothing particularly alarming. If I really wanted to say a lot about some of the thetas, I might want to run a few more samples, but it's not too bad. Yeah. You can pretty much get a quick look at some of the estimates. You can see how they, at the degree to which they are similar or different across the drugs as you look across the thetas, which would be sort of indicators of the potencies of the various compounds here. This again, this pretty much indicates that we don't have any real convergence problems. And here we go. Here's our fits to the data. And just let me orient you to some of it, some of the way I set this up. So the black dots here then are all of our data represented as fraction of patients with the VTEs. So I've converted back from the counts of VTEs so that everything's on a more comparable scale. So you can see the dose response and it expressed as a posterior median and 90% credible interval for our predictions. And we've got, you can see this VTE data is somewhat noisy, but the model seems to largely capture the most of this here, with the possible exception of this guy wandering off here. What's overlaid on top of that is each one of these studies did have an enoxaparin treatment arm, and that's shown a little bit differently. I use horizontal lines for all of the components. This sort of gray horizontal line that you see in each one of these is the observed fraction of patients that experienced a VTE on that particular treatment arm. And then the model predictions are shown by the dashed lines. Again, it's a blue dashed line for the posterior median, and red represents the 90% credible interval here. So you can get some idea on the extent to which that is or is not captured as we look across here. For the most part, it is. You can see there's an awful lot of intertrial variability in the enoxaparin outcomes here. Then we can go down, and this is our population prediction, or essentially predicting. This is essentially what you would predict for a new trial that had the same design for each one of these. So in this case, the enoxaparin is, excuse me, the enoxaparin arm is essentially the same for each one of the trials, except for some adjustment for sample size. So the medians are essentially identical, with the width of the credible intervals being shorter or wider depending upon how many patients were in the trials. Let's see. Whoops, I just pushed a button I didn't want to. Let's see. We'll undo it, whatever it was. There we go. What else do I want to show you? I suppose we can show the parameters in here. I don't think it lets me enlarge that. It lets me do it this way. I guess maybe one quick thing to look at is the effect of N over here. No particular alarms going off as part of this. This was, how many did we actually have raw in this? When I ran this, it was, okay, so we had 1,000 or 10,000 per iteration, or per chain. Kept 6,000 of them, but only kept every fifth of those. So that's what, 1,200. So there would be 3,600 total samples that was retained from the run. So you can sort of compare that to this. So you can see there's certainly some autocorrelation reducing the effect of N compared to that 3,600. You can see some, like EP hat, is nearly equivalent to a set of independent samples, but some are less, the worst being a couple of the thetas here. None of them are awful. Again, if you wanted to make, particularly precise inferences about tail probabilities, about the thetas, you probably want to run more so that you're well over 1,000, and depending on how much precision you feel you need in those, but it's not too bad, particularly since we didn't see any convergence issues with any of these. I suppose if we worked at it, we could probably make some inferences about those values, but I won't agonize over that right now. Okay, so let's see. Is there any more I want to say about that? Did I have any notes here? No, that's really pretty much a repeat of what we just saw here. So the main point here was, again, just to illustrate how you can model data like this in terms of a binomial distribution. Before we go to the next case, any comments or questions? Okay, why don't I just scoot on to the next one then? The next topic I wanted to hit on was, well, go ahead and maybe I'll mention here, was actually looking for a decent example of this case where we could take a look at the number of fraction of patients at each level of some ordinal scale. Didn't have anything handy, so I haven't done an example on that, so I'm going to let that one go for the time being. I'll keep my eyes open for a decent example of that. So instead, as I'm going to talk in terms of things where we're counting up events. And for this, I do have an example. So I had mentioned this before then, that you may have situations where the outcome that was measured in the original study was maybe some count of events within some specified period of time. So for example, that might be something like the number of seizures, and where you're looking at some treatment for epilepsy, number of emesis events. This is commonly encountered where you might want to count up the number of adverse events, something like that within each patient. And most often that sort of data then would be summarized as the mean number of events over the total study period, or maybe for some periods between study visits. And if we were modeling that sort of data at the individual level, typically for that sort of count data, we would be using something like a Poisson distribution to describe the likelihood, or possibly some variation on the Poisson distribution to deal for what's often termed over-disperse, the over-dispersed case. And just for those who haven't worked with that, in the Poisson distribution, the mean and variance of the counts is equal under the Poisson model. But we often find that when we look at the counts, that the variance exceeds, more often than not, it exceeds the mean. And we would refer to that situation, that distribution, as being over dispersed in comparison to the Poisson distribution. And there are various variations around the Poisson to deal with that. One particular one would be the negative binomial distribution, which is essentially a Poisson distribution where the average rate is gamma distributed. At least that's one way you can construct the negative binomial. But there are other variations around that I go over in the MI255 class. Another class of problem is one where there seems to be an excess of cases where you have zero events in there compared to the Poisson distribution, and there are special zero inflated Poisson models, often referred to as zip models, for dealing with that. So that's what you would do with individual data. How do we translate that in a context where we're going to be doing a meta-analysis where we've got a summary statistics, which is usually going to be something like a mean count across the patients. As I mentioned here, one approach that you can do would be to just sort of rely on the central limit theorem and the fact you're dealing with a mean, and then in the limit, a mean of a random variable would be could be approximated as a normal distribution. So we might just buy that and go ahead and use a normal distribution in that. As I mentioned, the only extra thing you would have to deal with in that is that the hazard for an event, well, the probability of an event is going to be different depending upon how long you observe the patient. So the average event count would change, would be greater for a longer period if the duration of observation was longer. So you do have to come up with strategies for adjusting for that appropriately, and that is actually, that's relatively easy to do under reasonable assumptions about what the hazard for an event is over time. Anyway, so that's one approach, and alternatively, another approach would be to take advantage of an addition property of the Poisson distribution, which says that the sum of Poisson distributed random variables is also Poisson distributed. So in here I just put that mathematical term. So if for all I, if theta I is Poisson with some mean lambda I, for all of those cases, then if you sum up all of those theta i's, that too is Poisson distribution, where the mean is the sum of those lambda i's. So that would be, so again, that follows from that if the individual count data are Poisson distributed, then the sum of those counts would also be Poisson distributed. And you could calculate that sum from the mean by just multiplying the mean count by the number of patients to get that. Now, I'm actually being a little bit sloppy in that statement. To some degree, that's assuming that, actually, no, I was about to say isn't quite true. I was about to say that that isn't quite true if the observation times are different. Actually, it's still true if the observation times are different. The problem is that you know, is how you would interpret the lambda i's. Anyway, we won't go too far into that. So what I want to do is do an example, and what I'm going to do initially is use an example using that second approach where we actually use the Poisson distribution as the approach for dealing with it. And in fact, that choice is going to lead to a suggested homework assignment for you, but more on that in a minute. So the example I'm going to use is some data I've got here that I've collected from published reports of migraine prophylaxis trials. And there's a number of different agents that you know, are used in an attempt to prevent migraine occurrences. You know, in other words, to reduce the frequency of migraines in patients. One in particular is topiramate, and that's the one I'm going to focus on in this example. So we're going to look at the effect of topiramate on the mean number of migraine days per month. So what I'm going to do is use some published data. So this is published data on the number of migraine days per month from 7 migraine prophylaxis trial in which 1 or more doses of topiramate were compared with placebo. And the way the results were reported is they're reported as mean number of migraine days per month across all of the patients. And you can see that plotted over here. So I've got migraine days per month on the y-axis, and the x-axis in these is topiramate dose, going from 0 up to 200 milligrams per day. And you can see, you know, as you're looking at this, there's at least some suggestion of a dose response. In most of these, you see things declining. You know, not so much in this one particular study, but but in the remainder of the studies, there's some indication of benefit. Just mention that how a migraine day is defined. There's a number of different measures of migraine frequency that are used. The one that we're looking at is termed a migraine day, and that's defined as any calendar day during which a patient had a migraine that lasted at least 30 minutes. So that's what would be categorized as a migraine day. So again, this is migraine days per month. So that's what we're going to model. Actually, this was kind of a quick and dirty, so this is definitely we'll call this a work in progress. So this is this proposed initial model, or I would call it really a very preliminary model. In other words, it's basically my first attempt without having done any further model exploration or selection here. So it's almost certainly a non-optimal model. So we're going to do a Poisson model for the total number of migraine days in the ICE treatment arm of the JAITH study. And when I say total, I mean total number of migraine days across all patients in that treatment arm for a given period of observation. So that's what this N then is going to be. That's basically taking the mean number of migraine days per month, multiplying that by the number of patients so that I get the total number of migraine days per month across all of the patients in that treatment arm. And in turn, I multiply that by the duration of observation in months so that it becomes the total count for that group of patients during this period they were within the study. So that's what this N is. In fact, I parameterized this much in those terms. So this is Poisson, where this mean here is going to be the Nij is the total number of patients. Lambda ij represents the model estimated number of migraine days per month per individual. And the delta Tj then is the duration of the observation period, typically the entire trial, except for a baseline period in here. So that's what we're going to attempt. The model I tried here is, now first of all, this lambda has to be non-negative for this to work. So one way to enforce that is I just use a log transformation here so that this number here, which is non-negative, when I take the log of it, then creates a value anywhere on the real line, and I used a linear model, linear function of dose as my first attempt. So admittedly naive, but good at first try as any. In fact, I probably should have made I actually did make a log plot where I did a log of migraine days per month versus dose to get a clue as to whether that might describe it. And it's not necessarily obvious from this, but it looks like it might be a suitable descriptor of what we've got there. Then for each one of those components, the only covariate I explored so far was the baseline migraine rate. And in particular, this lambda 0 sub ij is the mean number of migraine days per month during a baseline observation period in the same group of patients. So typically what's done in these trials is it's most often that baseline period is 4 weeks. So it's 4 weeks prior to starting the active treatment medication. So they usually do a period of 4 weeks observations, count up the number of migraine days. Generally, this is done by having patients fill out a daily diary to indicate whether or not they experienced a migraine, as well as capturing other information. So that's going to be an observed baseline measurement in this case. Again, averaged over all the patients. So I've got that. And so I'm going to do this as a linear function of the log of that quantity here. divided by 6. So it's basically like centering it around 6. So the way you can interpret this is if you like, is that this, let's see, how do we want to put it? Basically, you can think of this A1J as being the value of A when the baseline rate is 6. So it's just kind of centering it around sort of a typical value. And in fact, if we go back, you can say that with the exception of one trial that has particularly high rates of migraine here, the 6 is probably a good representative number as any when we look across these trials. Same thing for the slope, made that possibly dependent upon the baseline, and then incorporated inter-trial variation right now just in the intercept components here, the A1J and B1J term here, and then again both normally distributed. So again, that's just sort of a first let's take a shot kind of a thing at the model without too much exploration around alternative models to get there. Let's see, is there anything I missed a definition of? I think we got all the pieces there. So that's what the first attempt on this. Okay, so let's go ahead and just jump into it. And then maybe do a little critique of it as we go. Okay, so that, again, I supplied you with the version I ended up with. What the heck did I call it? There it is, migraine example. I guess that works. Okay, so again, we can take a look at what the data we're going to be working with looks like. Okay, so you can see I've got a study identifier here. You can see we're going to have to convert this to an integer sequence starting at 1 because that's not the way it's written here. We've got the daily dose, got a start and an end time. These would be the times over which the migraines were actually counted. The mean migraine rate, again, this is migraine days per month, taken as a mean across the patients, the total number of patients, and a baseline rate. So that's what we're going to be working with. So basically the over here is our lambda sub 0 in that last component, and we'll construct our what we've got labeled as, what did I call it, just migraine in the or end migraine, okay, from there. Okay, so that's the data we're going to work with. Let's go back and pull up the implementation of the model. I can see I was still working on this a bit up to the last minute here. I haven't even incorporated any nice comments here, so we'll just kind of have to work this one raw. Okay, so we've got our model. The likelihood component, here's our likelihood term right here. Guess I can stick that in here while we're looking. So we've got this migraine. So the migraine I, again, is going to represent the total number of migraine days across all subjects within that treatment arm. And that is being modeled as Poisson with a term here I just called lambda t in here, which is going to be specific to each treatment arm. And that lambda t, you can see this is where I calculated. I've got a lambda representing the model predicted monthly number of migraine days. dt is going to be the number of months over which those values were counted. And the n is going to be the number of patients within that treatment arm. Then here's where we've got our log lambda then is going to be our linear model. And then we've got our two components there, are intercept and slope, which are linear functions of the log of the baseline migraine count. So that's the core of it. And then we've got our posterior prediction, our individual prediction. The reason down here I've got the code for the population predictions. The reason why it's commented out at the moment is I kept on running into numeric overflows when I was trying to use it and haven't had time to debug that. And if we start thinking about it, there's actually there's a fairly evident reason why. If we think about the value that lambda t might take on for some of these trials, in fact, maybe we can go back to the study. So lambda t is going to be on the same order as the value on the left-hand side here, so it serves as a mean. And so if we start looking at values here and think about multiplying, so we've got a migraine days per month. So for example, if we start calculating the total number of migraine events for a given treatment arm, in fact, we could actually do that fairly quickly. That's going to be the migraine rate times the number of patients times the difference between the end time and the start time. And you start discovering we end up with some fairly big numbers over here. And if you remember the Poisson distribution, there's at least one place in there where it's going to be trying to put this number in as an exponent. So the potential for overflow is pretty big with these kinds of numbers. So there are some problems with using the Poisson distribution to describe this, not theoretically but computationally. So that's where we start running into problems where when the numbers are on that kind of an order and you start making them an exponent, all of a sudden things start blowing up on you. So start running into that sort of a problem. Well, more on that, where that might lead us in terms of maybe some better model choices in a minute here. For now, let's just go ahead and implement what we've got here and illustrate its use. Let's see, for priors down here, as part of the effort to try and keep from running into those overflows, I found myself being maybe a bit more informative on the priors than I normally would, although we'll see if you take a look at these priors compared to the estimated posteriors, they're still fairly weakly informative, but not as much so as I typically do when I truly want to be uninformative about it. And not a whole lot to say on that, but we can go ahead and run this. I'm not going to, let me show you what happens with this without actually running it, because this one, to get enough samples to do anything useful, it turns out it takes a while. The basic model doesn't take so long to run. It's just that it turns out there's an awful lot of autocorrelation here, so you have to do a lot of samples, which doesn't take hours, but it does certainly take several minutes. You don't necessarily want to sit here and stare at my screen over. So let's go ahead and show you, actually even before we show the results, maybe I should take a peek at the script that goes with it. The R script, that is. Okay, for stuff's pretty much nothing much. The data set's largely already organized in a way that we don't have to do much data management on here. The only additional thing I did here is create a sequential index for our trials to have, because we'll need that in it. So putting together the data after that isn't too much. The additional thing also that happens is right here, where I calculate the appropriate values to put in. Why did I have that? Okay, maybe oh, because these are in weeks. That's why. Okay, I was trying to decide. Actually, I should have, all of these, I should have divided them by 4. So they're not quite as bad as they looked right there. Forgot these were in the time here, the units of the time were weeks. So I needed to adjust for that. I was trying to remember why I had divided by 4 here, because I was supposed to have that to put it, because the rate is in terms of events per month. So I need the time to reflect that in terms of months. Okay, so that's about the end of that. Again, there's the DT component here. I have to use my end time and start time difference to get that. And after that, it's pretty much old news. Same sort of things as most things. Yeah, most of this we've used in other scripts here, so there's nothing particularly new after that. So let's take a look at the results. Okay. Now, oh, I know one thing I should point out even before I do that. Notice that in this run I ended up doing a fair number of samples. Where'd it go here? There we go. Notice that the number of iterations here is 100,000 per chain. So I did 100,000, throwing out the first 20,000 of each one for burn-in. So we're talking about doing, 300,000 iterations total, of which I kept every 50th after that. And in spite of all of that thinning and everything, notice that there's still an awful lot of autocorrelation evident in the A2 and B2 parameters in this thing. There's also some, even in some of the other parameters that have they're sort of like, have a lot of nice sort of fuzzy qualities on the on a long term, well, on a short term basis. You can see even there's a certain amount of sort of long term autocorrelation, that's sort of longer waves involved in those. So if we were going to stick with the model as is without any reparameterization or anything, we'd have to run quite a few more samples in order to use it for any kind of production purposes. More likely what we really need to do is refine the model. Though fortunately there's no apparent sign of gross failure to converge, in the sense that you don't see these, you see the chains intertwined, you don't see them wandering off to completely different places, but it's still, we'd have to do an awful lot more samples. Okay, let's see. We can get here. Let's see, is there much I can say about these? Probably not off the top of my head here. But oh, that's right. I forgot I did a pairs. Sometimes I do this kind of a plot in order to get a handle on whether or not there's a lot of correlation amongst the parameters, because that can sometimes induce a lot of the autocorrelation in the Gibbs sampler. And there's nothing really gross across here. There are a few signs of things, not surprisingly, A2 and B2 that showed a lot of autocorrelation are also pretty correlated with each other. You can see that here and here. Those are actually the equivalent plot, just switching the axes. So there is a fair amount there. There isn't a lot of apparent from some of the others. There's a few strange things. If you look at the standard deviation here, there's some things that are a little funny, but not grossly so. Okay, enough of that. Okay, here's our individual predictions. If we just looked at these alone, things look like they're more or less going in the right directions. You can see in general, we seem to have captured, the at least the inter-trial variation seems to be able to capture the different things in here. We'd have to see if maybe maybe there's some undue shrinkage towards the data here or not. We don't know just looking at this alone. And the general trend of capturing the dose response going from the 0 to the 200 seems to be there. Though we'd have to again we'd have to do a few more diagnostics, but we're able to use this approach to describe the data. Now, let's see. I know there were a few comments I was going to want to make on this. I think that was it for the, yeah. Just go ahead and open up the parameter estimates because they emphasize the issue around a couple of our parameters. In particular, if we take a look at the A2 and the B2 here, if we look at the effective ends, you can see they're pretty small relative to the large number of samples that we actually ran. So again, that just emphasizes that strong autocorrelation that's present, and that we'd have to do more on that in here. Now, a couple issues that come to mind. One, as I mentioned, we start running into numerical problems because the mean of that Poisson starts getting particularly large and is probably and causes some potential numerical problems when we try to work with it. There are probably ways around that, even still continuing to use the Poisson distribution, but my guess is, given the number of events we're actually looking at, is that using a normal approximation instead of going directly to the Poisson, even though that may be somewhat more theoretically attractive. The Poisson may be more theoretically attractive, but I think a normal approximation would probably have been perfectly adequate for the problem. So trying to be too obsessive about sticking with a count-based model is probably unnecessary here. So that's one side of it. Another thing is that it struck me after I did this that on further thinking, we've got a situation where maybe the Poisson model is not actually the more theoretically appropriate model either. Let's go back. Why don't I wander back to the slides here? And what I was going to get at when I think about this is thinking about the context here. Now, when we talk about Poisson distribution, a Poisson distribution describes cases where you're counting up events where there's theoretically a potentially infinite number of events that could occur within any given time frame. So within some finite time period under the Poisson model, you could still have a countably infinite number of events. Whereas with this particular context we're looking at here, that isn't true. Because of the way we've defined the endpoint. We're defining an endpoint again as that's written here. Let's go ahead and open this up. Here I'm talking about the definition for migraine days. So a migraine day is any calendar day during which a patient had at least, had a migraine headache, basically. And so the most number of migraine days you could possibly have would be the number of days over which the patient was observed. So if you've observed, like in many of these studies, patients over a 26-week period, the most number of migraine days you could possibly have would be 7 times 26. It can't be countably infinite, even theoretically. And given that, you could argue that a binomial model might be more appropriate, depending upon what you know about you know about the probabilities and how they might change over time. If we had probabilities changing over time, there's some variations around that we would have to do. But either way, the Poisson model is not the theoretically best one to use for that particular case because there is a known finite upper bound in this case. So anyway, that's a direction I might entertain doing, would be to look at this both as using a normal distribution to describe either something like migraine days per month, or since that has to always be non-negative, you could look at that directly, since it's a mean, and if you wanted to treat it as a mean, if you wanted to use sort of the central limit theorem as the basis for the argument, I guess you'd apply the normal directly to that, as opposed to some transformation on that. So that would be worth a shot. You'd have to make some variations on the way the model structure. You wouldn't be able to use that directly, would you? Let's see. I don't know, maybe I'd have to think about it. You might be able to use something pretty close to that. In this case, I wouldn't even bother working with the total counts. It's not worth. Yeah, you could just go ahead and use the mean migraine rate directly, rather than trying to adjust it for those time periods, and explore using that. So that would be one. And as I say, the other possibility would be, instead of having the total migraine counts being distributed Poisson, is instead use binomial, where the n in the binomial distribution would be basically the number of patients times the number of days that they're in the trial. And in fact, that leads me to what I'd like to suggest for homework. In fact, I'm going to basically add a component, given the comments I just made about the binomial. So we could sort of look at, 3 possible directions. I guess, these are of course not required homework, so you can sort of take on whatever component of it that you want. As a starting point, just go ahead and improve upon my somewhat non-optimal preliminary model, while still retaining that strategy of modeling the event counts as discrete random variables. In terms of like a Poisson-based model. That's one direction. Another direction then would be to implement a model using a normal likelihood, and as I say, then compare the results. And finally, given the discussion I just had, is you might also want to try modifying that approach for modeling the event counts, and instead of using a Poisson-based model, use a binomial model, and explore using that as an alternative. Again, that could be compared to a model using a normal likelihood. And let's see, that's actually coming pretty much to the end of my material for today. Let me again open it up to see if there's any comments or questions. And I guess while I'm waiting to see if there's any of those, maybe I'll also mention where we'll go next week. What I plan to do is go into the material I've got here about combining individual and summary data, depending on how much time I can carve out between now and then. I may expand what I've got to include a couple of there've been a couple of publications since I wrote this up that might be relevant to that topic. So I might want to drag those out and take a look at those and see what impact they might have on the approach that I'm that's described in the notes so far about how to deal with combining individual and summary data. Okay, don't see anything happening there, so I guess I'm going to sign off then, and look forward to talking to you. Well, I guess on Monday, or we can take a. I don't know how far I'll get around some of these options, but we can take a look at some of these possible competing models for the count data. I guess I'll talk to you then. Bye for now.